Good morning to everyone. Myself, P. Vanita, working as a assistant professor in the Sri Muthukumaran Institute of Technology. Today, we are going to see about the steering bridge. Steering bridge is an AC bridge mainly used for the measurement of capacitance and the dielectric loss of insulating materials. It operates based on the null deflection principle. This means that when the bridge is perfectly balanced, the potential difference across the detector becomes zero, and therefore no current flows through the detector. At balanced condition, the ratio of impedances of one pair of opposite arms becomes equal to the ratio of impedances of the other pair. This condition helps us accurately determine unknown capacitance and insulation properties. In this slide, we are discussing the construction and working principle of the steering bridge. The steering bridge consists of four arms, each having different electrical components. The first arm contains the unknown capacitor, denoted as Cx. Since the practical capacitor have dielectric losses, this loss is represented by a resistance Rx connected in parallel with the capacitor. So this arm represents the capacitor under test. The second arm contains a non-inductive resistor R3. A non-inductive resistor is used so that only resistance effect exists and inductive errors are avoided. The third arm consists of a standard loss free capacitor C3. This capacitor has a known and accurate value, which is used as a reference for comparison. The fourth arm contains a variable resistor R4 and a variable resistor C4 connected in parallel. These adjustable components help in achieving the bridge balance condition. A detector such as vibration galvanometer or headphones is connected between opposite junctions of the bridge. And AC supply is applied across the remaining opposite terminals. The steering bridge works on the null deflection principle. When the bridge becomes balanced, the potential difference across the detector becomes zero. Hence, no current flows through the detector. At this condition, the ratio of impedances of one pair of opposite arms equals the ratio of the other pair. This balance condition allows us to calculate unknown capacitance and the dielectric loss of the material. Thus, the steering bridge enables accurate measurement of capacitance and insulation properties using comparison with standard components. In this slide, we discuss the balance condition of the steering bridge, which helps us determine the unknown capacitance and dielectric loss. Let us first understand the quantities used. Cx represent the unknown capacitance to be measured. Rx represent the equivalent loss resistance of the dielectric material. C3 is the standard capacitor whose value is already known. R3 and R4 are resistance used in the bridge arms. C4 is the capacitor present in the balancing arm. The steering bridge operates on the null balance principle. When the bridge is balanced, no current flows through the detector and the potential difference across the detector becomes zero. At this balanced condition, the unknown capacitance is obtained as Cx equal to C3 into R4 by R3. This shows that the unknown capacitance depends only on known resistance and standard capacitor values. The dielectric loss angle is given by tan theta equal to 1 by omega C3 or 4. Here, tan angle represents the dielectric loss angle indicating insulation quality. Omega is the angular frequency is given by omega equal to 2 pi f. From these balance equation, we can determine unknown capacitance, dielectric loss of insulating material. Hence, a steering bridge is widely used for testing capacitors and insulation properties in high voltage equipment. Uh, the advantages of steering bridge has uh, several advantages is that it can measure both capacitance and dielectric loss Simultaneously, it provides high accuracy, especially for good insulating materials. It is suitable for high voltage testing applications. Also, the capacitance measurements is independent of frequency, which improves accuracy. However, the steering wheel also has some limitations. The circuit arrangement is comparatively complex and it requires a stable AC supply for proper balance. It is not suitable for materials having very large dielectric losses. A highly sensitive detector is required for accurate null detection. Then move on to the applications. A steering wedge is widely used in practical engineering applications such as measurement of capacitance of underground cables, testing insulating materials, measurement of dielectric loss in capacitors, quality control of insulation systems, and high voltage engineering laboratories. Although AC bridges provide precise measurement of resistance, inductance, and capacitance, practical factors introduce errors. These errors disturb the bridge balance conditions and reduce measurement accuracy. Therefore, understanding errors and compensation technique is very important. The major types of errors occurring in AC bridges are stray capacitance, stray inductance, frequency variation, temperature effects, detector errors, and contacts or lead resistance. Each of these effects affects the accuracy of bridge measurements. The stray capacitance exists unintentionally between bridge arms and air, between adjacent components, and due to leakage paths. These unwanted capacitance disturb the balance condition and introduce measurement errors. Stray capacitance errors can be minimized by using shielded cables, providing guard rings, applying proper earth shielding, and maintaining symmetrical circuit layout. These methods reduce unwanted capacitive coupling. Leads and resistors possess small inductance naturally at high frequencies. This inductance produces phase shift, which affects bridge balance and causes inaccurate readings. This effect is called stray inductance error. Next, the compensation for stray inductance. The stray inductance can be reduced by using non-inductive resistors, keeping connecting leads short, twisting the leads together, and reducing loop area in the circuit. These practices minimize unwanted inductive errors. AC bridge balance depends strongly on frequency. If frequency changes, reactance also changes, leading to the incorrect measurement results. Therefore, frequency variation introduces significant error. Next, the compensation for frequency error. Frequency errors can be minimized by using a stable frequency source, employing frequency independent balance equations, and balancing the bridge at the actual operating frequency. Next, temperature error. Resistance values vary with temperature. Heating effects cause parameter drift, which results in inaccurate readings. This phenomenon is known as temperature error. The compensation for temperature errors can be reduced by using lower temperature coefficient resistors, allowing components to reach thermal equilibrium and avoiding excessive current flow. Thus, we studied the steering bridge along with the different sources of errors in AC bridges and their compensation techniques. Understanding these errors helps improve measurement accuracy in practical instrumentation systems. Thank you.